So what we want to show today is that Tesla is much more than an electric car company, that we have deep AI activity in hardware, on the inference level, on the training level, and basically, I think we're arguably the leaders in real-world AI as it applies to the real world. And those of you who have seen the full self-driving beta, I can appreciate the rate at which the Tesla neural net is learning to drive. And so this is a particular application of AI, but I think there are more applications down the road that will make sense, and we'll talk about that later in the presentation. But yeah, we basically want to encourage anyone who is interested in solving real-world AI problems at either the hardware or the software level to join Tesla, or consider joining Tesla.
Okay, hi everyone, welcome. My name is Andre, and I lead the vision team here at Tesla Autopilot, and I'm incredibly excited to be here to kick off this section, giving you a technical deep dive into the Autopilot stack and showing you all the under-the-hood components that go into making the car drive all by itself. So here I'm showing the video of the raw inputs that come into the stack, and then neural network processes that into the vector space. And you are seeing parts of that vector space rendered in the instrument cluster on the car. What I find kind of fascinating about this is that we are effectively building a synthetic animal from the ground up. So the car can be thought of as an animal. It moves around, it senses the environment, and acts autonomously and intelligently. And we are building all of the components from scratch in-house. So we are building, of course, all of the mechanical components of the body, the nervous system, which is all of the electrical components, and for our purposes, the brain of the Autopilot, and specifically for this section, the synthetic visual cortex. So here are some of the results. So on the left, we are seeing what we had before, and on the right, we're now seeing significantly improved predictions coming directly out of the neural net. This is a multi-camera network predicting directly in vector space, and you can see that it's basically night and day. You can actually drive on this. And this took some time and some engineering and incredible work from the AI team to actually get this to work and deploy and make it efficient in the car. So here's putting everything together. This is what our architecture roughly looks like today. So we have raw images feeding on the bottom. They go through a rectification layer to correct for camera calibration and put everything into a common virtual camera. We pass them through RegNets, residual networks, to process them into a number of features at different scales. We fuse the multi-scale information with BiFBN. This goes through a transformer module to re-represent it into the vector space in the output space. This feeds into a feature queue in time or space that gets processed by a video module, like the spatial RNN, and then continues into the branching structure of the HydroNet with trunks and heads for all the different tasks. And so that's the architecture roughly what it looks like today. And on the right, you are seeing some of its predictions sort of visualized both in a top-down vector space and also in images. So definitely, this architecture has definitely complexified from just a very simple image-based single network about 3 or 4 years ago and continues to evolve. Now, in the beginning, roughly 3 or 4 years ago, most of our labeling was in image space. And so you can imagine that this is taking quite some time to annotate an image like this, and this is what it looked like, where we are sort of drawing polygons and polylines on top of these single individual images. As I mentioned, we need millions of vector space labels, so this is not going to cut it. So very quickly, we graduated to 3-dimensional or 4-dimensional labeling, where we are directly labeling in vector space, not in individual images. So here what I'm showing is a clip, and you are seeing a very small reconstruction. You're about to see a lot more reconstructions soon. But even this, we realized, was actually not going to cut it. Because people and computers have different pros and cons. So people are extremely good at things like semantics, but computers are very good at geometry, reconstruction, triangulation, tracking. And so really for us, it's much more becoming a story of how do humans and computers collaborate to actually create these vector space data sets. And so we're going to now talk about auto-labeling, which is some of the infrastructure we've developed for labeling these clips at scale.
So even though we have lots of human laborers, the amount of training data needed for training the network significantly outnumbers them. So we try to invest in a massive auto-labeling pipeline. Here's an example of how we label a single clip. A clip is an entity that has dense sensor data, like videos, IMU data, GPS, odometry, etc. These can be 45 seconds to a minute long. These can be uploaded by our own engineering cars or from customer cars. We collect these clips, and then send them to our servers, where we run a lot of neural networks offline to produce intermediate results, like segmentation masks, depth, point matching, etc. This then goes through a lot of robotics and AI algorithms to produce a final set of labels that can be used to train the networks. So a single car driving through some location can sweep out some patch around the trajectory using this technique. But we don't have to stop there. So here, we collected different clips from the same location, from different cars maybe, and each of them sweeps out some part of their road. Cool thing is we can bring them all together into a single giant optimization. So here, these 16 different trips are organized aligned using various features such as road edges, lane lines. All of them should agree with each other and also agree with all of their image space observations. Together, this produces an effective way to label the road surface, not just where the car drove, but also in other locations that it hasn't driven yet. We don't have to stop at just the road surface. We can also arbitrarily reconstruct 3D static obstacles. Here, this is a reconstructed 3D point cloud from our cameras. The main innovation here is the density of the point cloud. Typically, these points require texture to form associations from one frame to the next frame. But here, we are able to produce these points even on textureless surfaces like the road surface or walls. And this is really useful to annotate arbitrary obstacles that we can see in the world. One more cool advantage of doing all of this on the servers offline is that we have the benefit of hindsight. This is a super useful hack because, say, in the car, the network needs to produce the velocity. It just has to use the historical information and guess what the velocity is. But here, we can look at both the history but also the future and basically cheat and get the correct answer of the kinematics, like velocity, acceleration, etc. One more advantage is that we can have different tracks, but we can stitch them together even through occlusions. Because we know the future, we have future tracks, we can match them and then associate them. So here you can see the pedestrians on the other side of the road are persisted even through multiple occlusions by these cars. Combining everything together, we can produce these amazing data sets that annotate all of the road texture, all of the static objects, and all of the moving objects, even through occlusions, producing excellent kinematic labels. You can see how the cars turn smoothly, produce really smooth labels. All the pedestrians are consistently tracked. The parked cars have basically zero velocity, so we can also know that they are parked. So this is huge for us. In the early days of the network, we noticed, for example, in low visibility conditions, the network can suffer understandably because obviously this truck just dumped a bunch of snow on us, and it's really hard to see. And we sent this through our auto labeling pipeline that was able to label 10K clips within a week. This would have taken several months with humans labeling every single clip here. So we did this for 200 different conditions, and we were able to very quickly create large data sets, and that's how we were able to remove this. So once we train the networks with this data, you can see that it's totally working and keeps in memory that this object was there and provides this. So finally, we wanted to actually get a Cybertruck into a data set for the remove the radar. Can you all guess where we got this clip from? I'll give you a moment. Someone said it. Yes, it's rendered. It's our simulation. It was hard for me to tell initially, and if I may say so myself, it looks pretty. It looks very pretty. And since this is a simulation, it starts from the vector space. So it has perfect labels. Here we show a few of the labels that we produce. These are vehicle cuboids with kinematics, depth, surface normals, segmentation. But Andre can name a new task that he wants next week, and we can very quickly produce this because we already have the vector space, and we can write the code to produce these labels very, very quickly. We don't want to stop there. So actually, we want to recreate any failures that happens to the autopilot in simulation so that we can hold autopilot to the same bar from then on. So here, on the left side, you're seeing a real clip that was collected from a car. It then goes through our auto labeling pipeline to produce a 3D reconstruction of the scene along with all the moving objects. With this, combined with the original visual information, we recreate the same scene synthetically and create a simulation scenario entirely out of it. And then when we replay autopilot on it, autopilot can do entirely new things, and we can form new worlds, new outcomes from the original failure. This is amazing because we really don't want autopilot to fail, and when it fails, we want to capture it and keep it to that bar.
All right, thanks, Ashok. Hey, everyone, I'm Milan. I'm responsible for the integration of our neural networks in the car and for most of our neural network training and evaluation infrastructure. And so tonight, I'd just like to start by giving you some perspective into the amount of compute that's needed to power this type of data generation factory. We've been scaling our neural network training compute dramatically over the past few years. And today, we're barely shy of 10,000 GPUs, which, just to give you some sense, in terms of number of GPU, is more than the top 5 publicly known supercomputers in the world. But that's not enough, and so I'd like to invite Ganesh to talk about the next steps.
My name is Ganesh, and I lead Project Dojo. It's an honor to present this project on behalf of the multidisciplinary Tesla team that is working on this project. As you saw from Milan, there's an insatiable demand for speed as well as capacity for neural network training. And Elon prefetched this, and a few years back, he asked us to design a super fast training computer, and that's how we started Project Dojo. Our goal is to achieve best AI training performance and support all these larger, more complex models that Andre's team is dreaming of, and be power efficient and cost effective at the same time. This was entirely designed by Tesla team internally, all the way from the architecture to GDS out and package. This chip is like a GPU-level compute with a CPU-level flexibility and twice the network chip-level I/O bandwidth. If I were to plot the I/O bandwidth on the vertical scale versus teraflops of compute that is available in the state-of-the-art machine learning chips out there, including some of the startups, you can easily see why our design point excels beyond par. And here, we came up with a new way of feeding power vertically. We created a custom voltage regulator module that could be reflowed directly onto this fan-out wafer. So what we did out here is we got chip, package, and we brought PCB-level technology of reflow onto this fan-out wafer technology. This is a lot of integration already out here, but we didn't stop here. We integrated the entire electrical, thermal, and mechanical pieces out here to form our training tile fully integrated, interfacing with a 52-volt DC input. It's unprecedented. This is an amazing piece of engineering. Our compute plane is completely orthogonal to power supply and cooling. That makes high bandwidth compute planes possible. What it is a 9 petaflop training tile. This becomes our unit of scale for our system. And this is real. I can't believe I'm holding 9 petaflops out here. Next up, how to form a compute cluster out of it. By now, you must have realized our modularity story is pretty strong. We just put together some tiles. We just tiled together tiles. A 2x3 tile in a tray makes our training matrix, and 2 trays in a cabinet give 100 petaflops of compute. Did we stop here? No. We just integrated seamlessly. We broke the cabinet walls. We integrated these tiles seamlessly all the way through, preserving the bandwidth. There's no bandwidth divot out here. There's no bandwidth cliffs. All the tiles are seamlessly connected with the same bandwidth. And with this, we have an exapod. This is 1 exaflop of compute in 10 cabinets. It's more than 1 million training nodes that you saw. We paid meticulous attention to that training node, and there are 1 million nodes out here with uniform bandwidth. To sum it all, this is what it will be. It'll be a fastest AI training computer, 4x the performance at the same cost, 1.3x better performance per watt, that is energy saving, and 5x smaller footprint. This will be Dojo Computer. And we are not done. We are assembling our first cabinets pretty soon, and we have a whole next generation plan already. We are thinking about 10x more with different aspects that we can do, all the way from silicon to the system again. We will have this journey again. We're recruiting heavily for all of these areas. Thank you very much. And next up, Elon will update us on what's beyond our vehicle fleet for AI.
Dojo is real. The Tesla bot will be real. But basically, if you think about what we're doing right now with the cars, Tesla is arguably the world's biggest robotics company because our cars are like semi-sentient robots on wheels. And with the full self-driving computer, essentially the inference engine on the car, which will keep evolving, obviously, and Dojo, and all the neural nets recognizing the world, understanding how to navigate through the world, it kind of makes sense to put that onto a humanoid form. And we're also quite good at sensors and batteries and actuators. So we think we'll probably have a prototype sometime next year that basically looks like this, and navigate through a world built for humans, and eliminate dangerous, repetitive, and boring tasks. So, yeah, it's around 5'8", has sort of a screen where the head is for useful information, but it's otherwise basically got the autopilot system in it. So it's got cameras, got 8 cameras, and the full self-driving computer, and making use of all of the same tools that we use in the car. So, I mean, things I think that are really hard about having a useful humanoid robot is, can it navigate through the world without being explicitly trained? I mean, without explicit, like, line-by-line instructions. Can you talk to it and say, you know, please pick up that bolt and attach it to the car with that wrench, and it should be able to do that. It should be able to, please go to the store and get me the following groceries. Essentially, in the future, physical work will be a choice. If you want to do it, you can, but you won't need to do it. And yeah, I think it obviously has profound implications for the economy because given that the economy at its foundational level is labor, I mean, capital equipment is just distilled labor, then is there any actual limit to the economy? Maybe not. Join our team and help build this. Yeah.